Alors bonjour, merci beaucoup, merci Sylvain, merci Pierre pour l'invitation. J'aime beaucoup revenir sur Paris, donc c'est une bonne occasion. Et d'accord, donc voilà, le sujet de mon talk est celui-là, et la partie, disons, plus de recherche qu'il y aura dedans est faite en collaboration avec mon collègue Giulio Bonelli à la SISSA et puis Anton Sheshkin, his postdocs in SISSA. Paolo Arnaudo is presently postdoc in Southampton. He was a former student of us. And Cristoforo Iossa is a postdoc in Geneva with Alba. And instead, Daniel Panealiktig left physics, and now he's in Canarias, working for a company and doing surf and enjoying a lot. And okay, so let me state a bit what could be a basic question in quantum field theory and string theory, or in general, is that typically what we do is to study observables in terms of series, which are perturbative series in some parameter, which is so for example the gauge coupling, and then possibly with non-perturbative corrections. And one question that we can pose is whether these are local expansions of solutions of some differential equation, which can be linear, non-linear, or some differential equation. Why we pose this question? Because a positive answer to this question would be very useful, in the sense that would give access to a non-perturbative formulation on the theory, in the sense that by using these equations one can study global properties of this series as convergence, their connection coefficients, and then between different expansion, which means, for example, duality in these theories, and in some cases also exhibit some solutions in closed form, for example, an integral form.
Sorry, so you mean an equation in G or in some other parameter?
Even in some other parameters, yes. We will show this. There can be both. It can be equations in G. For example, these are the equations of Painlevé type, so they are non-linear, very complicated. The simpler equations are equations for in gauge theory. For example, you put a defect in the gauge theory, and then there are equations in the position of this defect in the space-time. So you really break Lorentz invariance, and you study the dependence on this. So in this talk, I'm going to present an instance of this, a case in which a positive answer to this question can be given, which is so-called Painlevé gauge theory correspondence. And this is a correspondence between a classical system on one side and a quantum one on the other, because states that the general solutions of Painlevé classical Hamiltonian dynamics can be given in terms of supersymmetric partition functions of SU2 gauge theories in 4 dimensions. Of course, Painlevé equations arose many times in the study of theoretical and mathematical physics. What I like about this instance is that it is systematic, in the sense that it concerns the full set of Painlevé equations, and actually it can be also generalized to more general isomonodromic deformation problems and also Q-difference problems. And it has some useful results in both directions. In one direction, from the gauge theory to the Painlevé story, gives for the first time a general solution to these equations in terms of some very explicit and concrete functions, which are built off the Nekrasov functions that Alba was explaining to us this morning. And in the other direction, the presence of, in this case, nonlinear ODE allows to give some hints on a non-perturbative formulation of gauge theory and topological strings. So on the questions, basic question I was posing at the beginning. So the origin of this correspondence, in the birth of this correspondence, an important role is played by AGT correspondence that was also mentioned this morning, and sounds much better in English than in French, AGT. So, historically, the connection between Painlevé equations and CFT2 was known for a long time from the Japanese school that introduced the notion of tau function and then showed that the function can be computed in terms of some correlators in CFT. And then the AGT correspondence linked CFT2 to four-dimensional gauge theories, and this opened the possibility to write an explicit solution for the general Painlevé equation in terms of the so-called now Kiev formula, because was did by Oleg Lissovig, Heun, and Yorgov. All them are original from Kiev, although Oleg is working not far from here in Tours. And so this is a bit the origin of this Painlevé gauge theory correspondence. And an interesting point, let me say a small remark about this. The original Kiev formula is formulated in the case in which these two parameters sum to 0, which means that B is equal to I, and then the central charge is 1. So it's a very specific case of CFT2, and it is a natural question to go out of this, not only for curiosity, but also because it's very useful for many problems. And so in this case, one goes to a formulation of quantum Painlevé equations, but about them less is known. And what we have been able, together with Anton, is to formulate quantum Painlevé equations in Hirota bilinear form, and then we studied this solution. But this is a work in progress. I won't say much about this in this talk. And there is also a geometrical viewpoint on this, which means to study the Hitchin system with generic twistorial parameter. So the standard Painlevé gauge correspondence is in the so-called conformal phase or upper limit of the Hitchin system, and then if you study the Hitchin system for generic twistorial parameter, then you go to these quantum Painlevé equations. And then the other part of the talk is about connection formulae and Heun functions. This is deeply related. Actually, as far as I know, the general Heun function was introduced precisely to study the Painlevé 6 equation. And Heun equations arise, are linear ODEs in this case, and arise under certain assumption from the linear system associated to Painlevé equations. And I will talk more in length in the second part of the talk about the connection formula for the Heun function, also because there are applications in the perturbation theory of black holes, in which this kind of machinery surprisingly works very, very well. And so let me give a bit the plan of the talk. So I will first recall a bit the formulation of Painlevé equations in the analytic framework. Then, in order to connect this to quantum field theory and to the recent progresses, it is needed to go to a geometrical formulation, as Alba also was underlining, stressing in this morning. And through going this isomonodromic deformation problem, the geometric formulation, we can go to quantum fields and then go to the various applications. So if there are no questions, I will start with the part of a review a bit of Painlevé equations. This is just to refresh our mind, it is very known that, oops, what happened here? Okay. Several linear ODEs define special functions. The basic example is the hypergeometric equation. Indeed, the Heun equation is the next generalization of hypergeometric equation. And then people already in the 19th century was trying to pose him the question how to define good special transcendental functions via non-linear ODEs, and then classifying linear ODEs, but non-linear ODEs, but with some property. And then it was observed by Poincaré, Kovalevskaya, that the solutions of the ODEs that appear in integrable systems are free from movable branch points. So this was thought to be the key point of the property of these ODEs. And then this led to the idea of studying the ODEs with Painlevé property, namely nonlinear ODEs whose solutions meet only movable poles. For example, here this is of Painlevé type because you can move the position of the pole by changing the initial conditions when you solve this equation, and this is of course not because you move here a branch cut. And then they started to classify, and the first order were classified by Fuchs and Poincaré, and there are only two types, which are the Weierstrass equation and the Riccati equation that was mentioned by Alba this morning. It appears in the study of the quantum periods in the WKB approximation. And then for the second order ODEs, it was an hard tour de force in analysis to classify them and to recognize by change of variables the equality among various different formulations. I think that at the beginning were more than 100. Now we know that there are only 6 of them, and this is the Painlevé 6, which is the most general one, which, as you see, contains some parameters and some rational coefficients with some poles. Then by moving these poles and changing these coefficients, one can go to through the so-called confluence diagram of Painlevé, which leads to all different kind of Painlevé. Of course, then the names here, there can be very different names. I'm sticking to this notation, but there are also other kind of names related to the symmetry properties of Painlevé, etc. But okay. So let me say that since Heun equation is strictly related to Painlevé by studying the associated linear system, there will be an analogous coalescent diagram also for the Heun equation. So now let me pass to the geometrical formulation of the problem, with the idea then to use this geometrical formulation to make a dictionary with quantum field theory and supersymmetric gauge theories. So Painlevé equation can be reformulated as isomonodromic deformations. So we have, as I said, a linear system. This is a 2x2 matrix, is a connection with some, let's say, regular or irregular singularities. For example, Painlevé 6 is related to a SL2 connection on a sphere with 4 regular points, and then by using SL2 symmetry, we can fix 3 of them, and then the only parameter that is left, the only modulus, is the harmonic ratio, which is this parameter t. And then one can pose the problem of deforming, moving this modulus by maintaining the same monodromy for this connection around the regular punctures. This is the so-called isomonodromic deformation problem, and this is the second equation, so the variation with respect to the monodromy, the parameter t. This is the equation of the linear system, the original one, in which one varies with respect to the coordinate on the Riemann sphere, where we put the punctures, the regular singularities. So consistency of these equations essentially means for a gauge theoretical physicist that the derivative of A is a gauge transformation by the parameter B, and then the consistence lead to Painlevé equation. And the two matrices, so the matrix of the linear system and the matrix of the gauge transformations, are known to be the Lax pair of the Painlevé system. And in the limit in which one send to zero the derivative part, one pass from isomonodromic deformation system to a isospectral system, maintaining fixed the eigenvalues of this matrix. And this is the spectral curve here. And this plays a very important role because, as you may imagine, we will identify this spectral curve with the Seiberg-Witter curve of the supersymmetric gauge theory. So let me say a few words about the reduction to the Heun equations. So we rewrite explicitly this linear system. So this is a 2x2 first order ODE. And then we can reduce it, of course, to a second order ODE by substituting for psi2 in this way. And of course, in this, we have this to divide by these coefficients of the matrix A12, and this introduces what is called the apparent singularity at the zeros of these coefficients A12. And then in order to get a sensible equation, one has to do the work of singularity matching. Namely, we impose that these apparent singularities go to zeros to the singular point of the Painlevé equation, which are 0, 1, or tau, or at infinity. So, in this case, once you impose this singularity matching condition, you reduce to a second order ODE, which is precisely the general Heun equation. The precise description of this mechanism was done not far ago by Dubrovin Kapaev. This is one of the latest work of Boris. And also other Painlevé equations, of course, has to reduce to various confluences of the general Heun equation. For example, for Painlevé 5, this was worked out in detail in this paper that was also mentioned this morning by Alba, in collaboration with Misha Bernstein and Pasha Gavrilenko. So now we have a geometrical interpretation of the Painlevé confluence diagram, because we translated it into an isomonodromic deformation problem on a Riemann surface. So we have the Riemann surface with 4 regular singularities, which is the one associated to Painlevé 6, but then we can collide these singularities and rescale the parameters in various different ways, and this will give rise to this Painlevé confluence diagram. In particular, these are irregular singularities of a higher and higher order in the lower part of the diagram. Okay, so now by using this, we are ready to pass to the dictionary with quantum field theory. And for the dictionary with quantum field theory, a good viewpoint is the one of higher dimensional quantum field theory. Actually, the highest superconformal quantum field theory one can formulate, which is the one in 6 dimensions, and is the one that lives on M5 branes in M theory. This is a 6-dimensional AR-1 superconformal theory with 2,0 supersymmetry, and has as a bosonic group the superconformal group times this rotation group. This rotates the direction transverse to the 5 brane. So the Coulomb branch is described by gauge invariant functions of this transverse direction, which are real scalars in the adjoint of the SUR group. But this, of course, it is a 6-dimensional theory. We want a 4-dimensional theories, so we compactify this on a Riemann sphere. And we do, so we consider this system not on R6, but on R4 times the Riemann sphere. And so the local geometry near these hyperplanes compactified on this geometry is the one of the cotangent bundle on the Riemann surface times R3. And then in this case, the superconformal group reduces to the one in 4 dimensions, and then the rotations in the transverse directions. And we can combine 2 of the real scalar fields in the transverse direction into the complex one, which is a section of the canonical bundle on the Riemann surface. So the Coulomb branch in this case is described mathematically by sections of powers of these canonical bundles, namely by holomorphic k-differentials on this curve. Okay? And we realize via this M5 branes realize an R covering of the Riemann sphere, or more in general over a curve C, with the sheets that are labeled by the eigenvalues of this one-form field. So in this way, we recover a spectral curve, which is described by this equation. And this is the key result, because this spectral curve gets identified with the one associated to the lax connection of the isomonodromic deformation system. So this sets the dictionary between the two problems. And more in detail, if we do a further compactification on S1, the theory becomes on R4 times the S1 becomes a 5-dimensional Yang-Mills theory, and the vacua, which are invariant under R3, so they are vacua on C, are described by these Hitchins equations. And these equations can be reformulated in terms of the flatness of an SL-R connection, which is this one, which combines the connection one form on the Riemann surface and the scalar field, which is again a one form on the Riemann surface. And these equations, in the upper limit, they are precisely the ones of the isomonodromic deformation problem. For example, the radial component of the flat Hitchin connection on a cylinder with regular singularities obey Toda equations. And for 2 and 5 branes, this is nothing but the Sine-Gordon form of Painlevé 3 equation. So we have this dictionary between the isomonodromic deformation problem associated to Painlevé and the gauge theory. So we have the Riemann sphere on which we study the isomonodromic deformation problem, which corresponds to what is called the Gaiotto surface in gauge theory, namely the curve on which the M theory is compactified. The twisted kappa connection in the isomonodromic deformation gets identified with the upper in the gauge theory, and then the Painlevé time get identified with the gauge coupling. So in this case, the equation, as C1 was asking, is precisely in the gauge coupling itself. Okay? And then the Painlevé free parameters are matched with the masses of the n equal to theory, or in other words, the masses corresponds to the monodromies of the flat connection on the sphere.
Can you explain again this upper limit?
Ah, yes. This is the limit in which you send the radius of the S1 to 0 and the twistorial parameter also to 0 in such a way that their ratio is finite, and so this gets identified with the kappa parameter of the isomonodromic system, which twists the connection.
You lose some information in taking this limit.
Exactly, yes. And if you want to recover it, then you have to pass to the quantum version of Painlevé equations, in which the monodromy space is not classical, but is quantized, and the monodromies along A and B cycle no longer commute. And so this is the list of differentials that arise in this game. And if you want, these are the list of the potentials of the associated Schrödinger equation if you study the linear system associated. So from NF equal to 4, you can go to NF equal to 3 through the so-called holomorphic decoupling limit, in which you send the mass of one of the particles to infinity and the coupling of the gauge theory to 0 in such a way that the product is fixed. And from the Painlevé, in the Painlevé language, you redefine the monodromy of the connection and the time. As such, the product stay fixed, and so this fixes the new time of Painlevé. This is an easy limit and produces all the theories from NF equal to 4 up to NF equal to 0. But there are also more complicated limits, which are the ones that leads to higher irregular singularities, which are in gauge theory points which are super conformal point in the Coulomb moduli space, which contains particles, light particles, both with electric and magnetic charges, and as such is we don't know at the moment a Lagrangian description for them. So these are more difficult, and for them, as Alba was mentioning, there are not these special functions like I mean there is not a combinatorial form for the special function. There are other ways to compute them, but for example the issues of convergence are less understood. So to finish this part, then we have been able in this way to identify the geometrical formulation for the Painlevé problem into the renormalization group diagram for quantum field theories. And so these are the Lagrangian quantum field theories with the ones in which NF appears. This is the number of flavors. So you go in lower and lower number of flavors. This morning Alba was discussing this corner here. And then there are also these super conformal field theories strongly coupled, which are the so-called Argyres-Douglas points. They were first discovered by Argyres and Douglas. Okay, now let me pass to the description of the Heun connection problem in terms of these diagrams, etc. And for this it's very important to use the AGT dictionary. So we want to find the description of the supersymmetric gauge theory in terms of two-dimensional conformal field theory. And so just to set the notations, I recall for you the Virasoro algebra, on which the Hilbert space of Liouville conformal field theory in two dimensions is based. And in particular, the AGT dictionary states that the central charge of the Virasoro algebra is related to the equivariant parameters epsilon 1 and epsilon 2 of the gauge theory in this way. So you see that making limits on these parameters means to setting the central charge to some particular value in the Virasoro. And then we introduce the primary operators of the Virasoro algebra with some momentum alpha I inserted at x. So how can we describe the curves, the Seiberg-Witten curves, or if you want the Hitchins spectral curve in terms of conformal field theory? This can be done by describing the quadratic differential associated to these curves. So you have, in the case of SU2 gauge theory, you have a double cover. So you have just a quadratic differential on the Riemann sphere. And this quadratic differential can be constructed in conformal field theory by using the insertion of primaries in the conformal block of the energy momentum tensor with primaries, because we know that the OPE of the energy momentum tensor with Virasoro primaries produces precisely regular singularities. This is the key point. So in the limit of both epsilon much smaller than the conformal dimension of the primary, so both epsilon going to 0, which is precisely the Seiberg-Witten limit from the viewpoint of gauge theory, this conformal block, normalized conformal block, approaches the quadratic differential of the corresponding Seiberg-Witten curve. So, for example, to build the Seiberg-Witten curve of superconformal SU2 gauge theory with NF equal to 4 hypermultiplets, I have a quadratic differential with 4 regular singularities, because I had the sphere with 4 regular points, and then I have to consider Liouville correlator with the insertion of 4 primary operators. Okay? So from now on I will concentrate on that and then discuss later the confluences, because they need to introduce new ingredients in the conformal field theory itself. So, we have seen this morning an explicit presentation for the supersymmetric partition function in terms of Young diagrams, and AGT correspondence states that this very same combinatorial expression can be used to describe conformal blocks of the Virasoro algebra. In particular, this is the 4-point conformal block. And so the external momenta of the Virasoro conformal block get mapped up to linear combination to the masses of the 4-dimensional gauge theory, while the internal momentum get mapped to the Coulomb parameter of the gauge theory. And so we have a very explicit presentation for the conformal block, where I have an expansion in the position of one of the 4 insertions, which is the only one that is free, is a modulus, and a series with some combinatorial coefficients, which has been described more in detail also this morning. Okay? Together with the convergence properties. So now it is very important for us to see what is the behavior of these conformal blocks in the semi-classical limit, which means that I send the central charge to infinity. And one of the good points of AGT correspondence is that by using this very explicit combinatorial formula, allowed to prove a earlier conjecture made in CFT by Polyakov and Zamologikov on the fact that the conformal blocks in the quasi-classical limit exponentiate. So if you do the limit of the parameter b, which goes to 0, which is equivalent to say that the central charge goes to infinity, and you send the momenta to infinity in such a way that the product of this b with the momentum is finite, and this from the Greek letter I pass to the Latin one, then you get that the conformal block exponentiate in this way. And what appears in the exponential of the conformal block is precisely the Nekrasov-Shatashvili function that Alba described in her lectures. This has, unfortunately for now, just an indirect definition in terms of the Nekrasov function. So you have to compute the full Nekrasov function, then multiply by b square and sending the limit of b to 0. Nonetheless, you can do this computation to high orders in the t parameter, and you have very explicit expressions for that. So why these are important? Because it is known that, let me say it in brief, then I will present more the explicit formula in the following. The point is that we know that in conformal field theory the correlators obey Fuchsian differential equations if you insert what is called a null state operator. Then you use the conformal word identities to have some PDEs which are satisfied by the correlator. And what happens is that if you go to the semi-classical limit for the 4-point, the PDE reduces to an ODE, which is precisely the Heun equation, and you gain directly as a bonus that you know what is the function that satisfies this equation, and you know also what are the properties of the connection properties from the crossing symmetry of CF2, or also from the fusion rules of the corresponding conformal blocks. Namely, you can fuse the degenerate field, so the no state, either with the primary, say, at 0, or you can fuse it with the primary at 1, and the two conformal blocks will be related by some fusion rules, which are rather simple, as I will show you. And this will provide a connection between the local expansions of differential equation in around z equal to 0, or the local expansion around z equal to 1. Okay? So this is from the conformal field theory, you will get directly the solution of the equation as a local expansion around different points, and then also the connection between these different expansions. So to give just the first basic example, if we study the 4-point correlator in which one considers 3 regular singularities and 1 degenerate primary operator, so 3 primary operators of generic form and 1 degenerate on the sphere, one gets directly an ordinary differential equation, which is the following one, and this is an ODE with 3 singularities on the sphere, which we know very well that is solved by the Gauss hypergeometric, and then the crossing symmetry of the conformal field theory relates different local expansion, for example, the expansion around 0 and the expansion around 1. So more explicitly in formulae, we have these 2 different 4-point conformal blocks with 1 degenerate, and the fusion kernel, which is known explicitly, which is given by this ratio of gamma functions, and this is precisely giving the connection formula for the Gauss hypergeometric function. So here we don't have even to take any semi-classical limit, everything is very simple because we are studying a very simple object. If we go to higher point correlators, so we pass from 4 to 5 points, then things becomes a bit more elaborated, but also more interesting, because you get the 5-point conformal block with 1 degenerate in session, and now the Belamin-Polyakov-Zamolodzi coefficient is a true PDE in the position of the degenerate field and also in the position of one of the primaries. And so we have the partial derivative with respect to this. And this is the new modulus. So the system is no longer rigid because the local monodromy exponents, which are the external momenta of the conformal block, are not enough to describe the local expansions of the functions, but we need also the information about this internal monodromy, this alpha. But thanks to the GT correspondence, we have an explicit combinatorial expression for this object, at least in some limits, and so we can take advantage of this to go to the Heun equation. So the Heun equation, as I said, appears in the semi-classical limit. So in the semi-classical limit, this 5-point conformal blocks exponentiate, as we were saying, and due to the presence of the degenerate field, this gives rise also to this extra term. And so the normalized semi-classical block, which is the one with the insertion divided the one without the insertion, has this local behavior here, okay, which is dictated by the local monodromy exponents. Now here I'm expanding around z equal to 0, and so A0 is the monodromy around that point, but also by this contribution of the Nekrasov-Shadashvili function, which takes into account, if you want, the internal monodromy along the internal channel. And so this object here obeys precisely the general Heun equation, which is the equation with 4 regular singularities, 0, 1, infinity, and the position t. And it has what is called the accessory parameter, which is a quantity which is not fixed by the exponents of the local solutions. And this quantity is instead determined by the Nekrasov-Shadashvili function. So now we want to make a precise connection to the Heun formulae, so we have to do a bit of dictionary to put the Heun equation in the standard notation, also for the functions that, for example, are used in Mathematica. And then this is the dictionary between the parameters of the Heun equation and the parameters of a conformal block. And in particular, these are just trivial linear combinations, but what is instead the important novelty is the fact that we have some explicit combinatorial expression for the accessory parameter U0, given in terms of the Nekrasov-Shadashvili function and its derivatives. So we can write a basis of solutions around 0. This is the general Heun function, which starts with 1 and then has a linear expression in Z, etc. And then this can be rewritten in terms of semiclassical blocks. So the local expansions are local expansions of semiclassical blocks. And now we can derive the connection formulae from the connection formulae for the semiclassical blocks. So you see that an important point is that the crossing symmetry or fusion rules are local. So for example, here the rules for the connection formulae are precisely the same as for the theory with one less insertion, or even you can put a long chain of insertions here, but nothing will depend on them as long as we study the local behavior of the conformal block, namely we exchange two neighboring insertions. Okay, so if I do the connection problem between 0 and t, this is universal also for several a Fuchsian problem with several regular points, and it's always given in terms of the matrix of the hypergeometric. But what changes is the normalization of these functions, because this contains the derivative of the prepotential, and so this is the object that appears also in the connection formulae. So essentially the new ingredient that appears in Heun functions with respect to the hypergeometric for the connection formulae is we have the standard gamma functions as before, but their argument is described in terms of the internal momentum, which is the quantum period of the Seiberg-Witten curve. And there is also this exponential term which depends on the local normalization of the semiclassical blocks, which depends on the points in which you're sitting. So for example, here you see that the local normalization around 0 is derivative with respect to A0, and instead the one with respect to t is derivative with respect to at. And so this term do not cancel but contributes in a crucial way.
Sorry, Alessandro.
Yes.
No, you want to derive the connection formula from this basically AGT relation.
Yes.
But the basic thing you've done is to relate the Heun equation to the BPZ equation. So then you are in conformal field theory for these blocks. We also already have formulas from Poisson-Techner for the connection of these conformal blocks. And could you alternatively use the Poisson-Techner formulas to get the same result about connections?
I think that, but you mean this is the connection formula for general blocks.
Yes, but from that you can deduce what you want.
Yes, in principle, yes. I think that you can. It is a possibility. That, but of course, in this way, is much simpler because you work for the specific problem you are interested in, and then you work it out directly without solving a much more general problem and then extracting the one you are interested in. But in principle, I think it can be done. Yes. Could be even interesting to do, yes. Okay, so let me make a general comment then about the two connection problems. You see that for the hypergeometric theory, you have a very rigid system. Once you fix the local monodromies, so the local exponents of the Frobenius solutions around the different points, you basically fixed everything, and then also the connection problem just depend on this, okay? But this is not the case for the Heun equation, and this is because in this case we have an extra modulus, we have an extra insertion, and so a fourth regular singularity, and so the connection problem is solved again in terms of gamma functions, but these gamma functions do depend not only on the local exponents of the various regular singularities, but also on this internal monodromy, which is also called the Floquet exponent for this differential equation. Okay, so this makes a big difference. So makes this second system much more difficult, and indeed, I mean, explicit formulae now we know them thanks to this correspondence with supersymmetric gauge theory. So now we want to pass to the confluent cases, and so as I anticipated, also for Heun, but what is that? Come si trova? Ah, okay. There is the analog confluence diagram as for Painlevé, because the underlying geometry is precisely the same. And as for Painlevé, the upper part of the diagram is all controlled by perturbative gauge theories. So we have all our Nekrasov-Shataishvili function, combinatorial formulae, etc. So it's very nice. The lower part is less known because they are irregular points of higher irregular singularities. But also to describe these irregular states, one need an extra ingredient, which are irregular states in the conformal field theory. And these are less known because before the advent of AGT correspondence, it seems that people do not care too much about this possibility, namely to collide primaries to get points which have a higher degree of irregularities. Let me come back to the construction of the Seiberg-Witten curve. If you remember, to construct the Seiberg-Witten curve, we had to insert the energy momentum tensor with a primary operator in such a way that the OPE gives a quadratic pole. And this gives a quadratic differential from the conformal block with a regular singularity. So if we want an irregular singularity to describe, for example, now we have the list of quadratic differentials much before here. So you see that here we have higher singularities, okay? And then, for example, here you have the higher singularity which sits at infinity. And what you want is to generate higher order singularities in the conformal field theory. And so this means that you have to build new states, and these are the so-called irregular states. And you can build them directly from by direct construction on the Virasoro algebra. by imposing the conditions you need. So you need that essentially for a singularity of order n plus 2, that the nth Virasoro generator that for primaries annihilates the state, in this case is different from 0, it has an eigenvalue different from 0. And then you impose that the rest of the generators gives 0. So in some sense these states are the analog of coherent states for the Virasoro algebra. And the constraints can be solved either imposing the state to be a common eigenstate of L1 or Ln, or an alternative formulation, which is equivalent, is to diagonalize the Virasoro generator from Ln divided by 2 to Ln. Okay? And this state can be also taught geometrically as arising from the collision of primary states, 2 or more primary states, with some rescalings of their momenta in such a way that you get that the singularity takes precisely the desired form. Okay? And in general they are called rank n divided by 2 irregular states. There is also, let me mention, purely algebraic construction of some of these irregular states in terms of algebra, of Virasoro algebra, that was done by Nagoya. But a systematic description of these states is not available at the moment, and there are also a systematic description of CFT involving these states is lagging at the moment, and so I urge the experts here to study the problem, which is interesting. So let me, what is interesting for example, for confluent Heun, which has many applications in the gravitational backgrounds, is the case of rank 1 irregular states. So in this case you diagonalize L1 and L2. Instead it's not a diagonal state of L0, so it's not a fixed conformal dimension. This comes from the collision of two regular singularities. So you can think that you collide the singularity at t and the singularity at infinity, and then you rescale the conformal dimensions in this way. By doing this, you get a state which is characterized by this action of the Virasoro generators on the algebra. Now I'm using the adjoint Virasoro operators because they are acting on the bra state, okay, at infinity. This rescaling is precisely the holomorphic decoupling in gauge theory. So we pass from nf equal to 4 to nf equal to 3 gauge theory by sending one of the masses to infinity and decoupling to 0 in such a way that the product is constant. And in the case of presence of a irregular state, not surprisingly, we get not hypergeometric, but confluent hypergeometric, in this case with Tagger function. So if one studies just the conformal block with one irregular state of rank 1 and then one primary state, and in section 1 degenerate, the corresponding conformal block is essentially up to factors the Witt-Tagger function. As before, for three primaries, we had the hypergeometric. And then we can connect this with the expansion at infinity, and not surprisingly, being careful to the Stokes sectors, because here now for irregular singularities one has to be careful to the angular sectors in the complex plane, one gets precisely the connection coefficients for the Witt-Tagger functions. And then one can repeat the game. For example, one can study 1/2 irregular state by a further reduction of the rank 1 irregular state, and then find the connection formula for Bessel functions, for example, and so on. And now let me go to confluent Heun. For confluent Heun, we consider this block in which we collided two of the primaries. So before, if you remember, we had the 5-point blocks with one degenerate. Now we collided two of the primaries into this rank 1 irregular singularity. Okay? So the connection problem between 0 and 1, it's very simple because, as I said, is one-step problem, and the resulting connection matrix is very similar to the one that I showed you before for the general wave function, nothing new. But here there is a novelty which is important if you want to connect to instead infinity, for example. Then, for example, if we want to connect the one conformal block expansion of the degenerate which fuses with the 1, so the expansion around z equal to 1, and the expansion around z equal to infinity, this has to be done with two steps because I have to cross two states, and so there is an intermediate step, which is this one, and then a final step, which is this one. So the connection problem get composite, and we have at the first part, in this part here, we have, as we saw, the connection problem similar to the Whittaker function, so the n matrix, and here instead, for this step here, we get the ordinary matrix of the hypergeometric. So if we do this composite procedure for the confluent Heun, and we introduce the suitable dictionary here, which is given in these terms, so the confluent Heun with the suitable normalization is this conformal block with this factor here, and then this is the dictionary for the various parameters of the Heun with respect to the conformal block or supersymmetric gauge theory. Then we get this formula, and you see, for example, that the Heun function at infinity is given by a combination of the two Heun functions which are a basis of the solutions around 1, but each of them has a coefficient which has two channels. Okay? And this has important implications also for the application to gravitational problems, because typically, as also Alba was saying, when you connect one function to another domain, you want that one of the two functions here, the one that behave badly under the boundary conditions you impose, gets killed, which means that you want to kill one of the two connection coefficients. But here you see that when you kill one of the two connection coefficients, you have two channels, and these two channels have an interesting physical interpretation in terms of near horizon, something that happens near the horizon of the black hole or far from the horizon of the black hole. And I think that Fabian is going to comment on that in his talk when applying this kind of formula for the black hole scattering problem. But so I'm not going to tell more about that. And I think that I'm almost at the boundary of the time. So let me just say that also other confluences can be studied. So we said that in the talk I presented the regular Heun, general Heun, and the confluent Heun. But and then here is the dictionary with all the other cases. So reduced confluent and doubly confluent, they correspond to two different versions of NF equal to 2 theories, and then reduced doubly confluent and doubly reduced doubly confluent correspond to the NF equal to 0, so the simplest case, although the name is the longest. And then there are also the other Heun equations which are at the bottom of the confluent diagram, and are related to the what are known as Argyres-Douglas points in the quantum field theory, so these ones here. So in principle, the connection formulae for those can be worked out in terms of irregular conformal blocks, but this is something that has still to be done. And it seems also that, at least for what I saw, there are no very strong applications of this, at least in the gravitational physics literature.
Sorry, Alessandro, what do you mean by NF equals to 2 symmetric and asymmetric?
Yes, this is, I can show you in the diagram, maybe already here.
Two representations of the same?
Yes, it is the same representation of the same theory, which are these two corners here. So here you collide from NF equal to 4 to NF equal to 3. Of course, you can choose whatever regular singularity you want, and you make to collide with another. It's completely symmetric. But once you go here, then you see that the situation is less symmetric, because you can choose either to make to collide the regular singularity with the irregular one, and this is the asymmetric presentation, which is this one. And this gives a kind of quadratic differential. And but you can also repeat the collision you did here. For example, you collide 1 with infinity, you get this, and then you collide 0 with t, and you get this. And this is the symmetric representation. And this is a different quadratic differential. So the physics is the same, but the Seiberg-Witten curve is apparently different, and the kind of equations that you study are different.
But the solutions are related also by some connection formula?
Not that I know, because they are different equations.
Laplace transformations, it's the two Lax pairs for Painlevé 3.
Exactly, these are the two different...
I had a slightly different question. These actually have loads of other representations of higher rank, which are still isomorphic. Do you still get, physics interpretations of those as well?
You mean the changing the gauge for the Lax connections?
Typically, each Painlevé equation has like an infinite number of Lax representations of arbitrarily high rank.
Exactly, yeah, I agree.
These are the ones of rank 2.
Yes.
There's lots of others.
Yeah. But these are the ones that connect to the Seiberg-Witten curve, and so you have to choose. In order to connect to the Seiberg-Witten curve, you have to choose a gauge in the Lax formalism.
Right, but if you look at, say, SU3, there'll be a Lax representation of Painlevé 6 for SU3. Have you looked at those in the physics as well, or not yet?
But higher rank?
Yeah, arbitrarily high rank. There's a representation of Painlevé 6 of arbitrarily.
No, because I thought that arbitrary rank you can formulate for a higher rank isomonodromic deformation, and then you have a correspondence with gauge theory with higher rank gauge group. This, yes, this you can do, and you can do even any general compact Lie group for the viewpoint of gauge theory. So not only SU, but also SO, SP, or exceptional groups you can do. And you can rewrite what are the bilinear equations and the solutions for the isomonodromic tau function. This can be done. Okay, so I think that it's time to finish. So let me conclude with, I didn't have time to talk about quantum Painlevé and its expansions. So let me just make two final remarks that, if you have the patience. So I didn't have time to talk about the topological string story, but so one can show that the Painlevé tau function, from this gauge Painlevé correspondence, you can work out a new expansion for the Painlevé tau functions, which are different from the Kiev formulae, and they are nice because they are expanded in terms of modular functions. And you can show that these solve holomorphic anomaly equation for topological strings. So I know that Ideal Maitaras, who is a PhD student at SISSA, will talk about that in LPTH very soon. So in case you are interested, you can hear his talk. And then let me say just briefly that Heun connection formulae from Virasoro blocks and supersymmetric H theories have been applied to a number of problems in perturbation of black holes, and also in more phenomenological ones and more theoretical ones like ADS-CFT, or one loop effective action for Euclidean quantum gravity. And the fact that there are analytic formulae and the presence of the gauge theory dictionary gives some new information. For example, it's not only computational fact, but you gain information about symmetry properties that maybe you would have missed in a simple, in the direct gravitational formulation. And also, for example, this splitting of the channels in the connection formulae gives a good guideline for the separation of scales in the physical problems. So this is something that I find nice. So the true question is if is there a physical motivation for this unreasonable effectiveness of this complicated supersymmetric gauge theory, string theories, and so on, in the application to astrophysical, so very concrete astrophysical problems in black hole perturbation theory. But maybe for answering this question, we need some extra help. So I thank you.
From the practical point of view, it's not very effective, actually, to compute physical quasi-normal modes. What I saw is a very low accuracy computation of...
Yes, maybe, I mean, compared to the numerics for the, if you want to do a very precise determination of the quasi-normal modes, the numerical approach is strong.
The continued fraction expansion?
Yes. Continued fraction expansion, for example, converges more efficiency. But what as in some application seems to be nice is that you can also study the global properties, so global analytic properties of the connection problem. So the fact that you have these functions, you can say something about their global properties and their dependence, for example, on the spin or on the physical quantities, and you can draw some conclusions on that. I think that, for example, Fabian will talk about this in the specific case of black hole scattering for Compton scattering of Kerr. And analogously, in the DSFT case, you have information about analytic properties of thermal two-point functions that confirm some expectation before, but from concrete computations and so on. So, okay.
Okay, one more question before the break.
There was this slide where you said that the Painlevé-Kovalevsky property was also due to Poincaré. Is there a particular paper where he speaks about it, or?
You mean a paper by a paper?
Poincaré and Kovalevsky observation that integrable systems often have solutions.
Yes, yeah. This you have to ask to some historian of mathematics. I don't know.
Kovalevsky was close to Weierstrass, I heard, but I didn't know that Poincaré had an input here.
No, I cannot refer to a specific paper. No, not now. I can. I don't remember now. Okay.
We have the complete works of Poincaré.
So you can check.
Okay, well, thanks again, Alessandro.